In this video, we'll be working a problem involving energy. You have a 5 kilogram block and is placed on a frictionless inclined plane. The block is pushed back into a compressive spring 0.6 meters as shown. Assume the spring has a spring constant of 200 newtons per meter. How far up the incline will the block travel? Alright, so again, as always, work non-conservative is equal to the change in the energy of the system, which is EF minus the energy initial. We're going to start with this block having been pressed back to some new X initial. That's 0 meters. And then this block is going to slide up to some place like up here, and that will be our final X position. Now, a couple of things to note. It doesn't say whether or not the spring stays attached. I will assume, and I know because I've seen the particular book where this was, I will assume that the spring is not attached. So not attached to block. In other words, at this point right here, there's some sort of platform, and you press it back, and then when it gets to 0, it releases it, and the block goes by itself up the incline. You could, of course, drill and attach the spring, and then it would stretch the spring. That would be a different type of problem. Now, if we take a look at the block, as the block moves at various times, for instance, initially there's going to be some friction force of the spring. Sorry, not friction, spring force. There's going to be some normal force. There's going to be some gravitational force. And that's it. Now, the normal force does no work. It's perpendicular to the displacement. The displacement in this problem, the delta R, if you will, is in that direction along the plane. The spring does work, but springs are conservative forces. The weight does work, but it's a conservative forces. So the only potential non-conservative forces is the normal force, and it does no work. So I can say the work by non-conservative forces is 0, and therefore the final energy has to equal the initial energy of the block. It is important that you go through this step in order to be sure that this is true. If it's not true, if you just jump to this statement right here, and there is work by non-conservative forces, for instance in what are called inelastic collisions in the next chapter, then you'll get the problem wrong. Now, in working one of these final versus initial, you need a couple of drawings. I like to call them before and after pictures. They're kind of like those Weight Watchers commercials. So here's the block initially, and it's at some location. And because gravity's in this problem, I'm going to say its initial Y position is 0. And I have to give it an initial X position. And I'm going to give it an X position. And it says that it's compressed 0.6 meters. So that's minus 0.6 meters. Remember, if you use the Hooke's law, you have to use it where X equals 0 is along is at the uncompressed position. Now notice that the funny thing now is that this thing is going to go in that direction. Its initial velocity, VI, is 0 meters per second. It's at rest. But as it moves along this direction is X. This direction is Y. Y and X are not perpendicular anymore. They don't need to be. The whole point about this is the fact that this is in the direction of the spring, and that's what we're using for the spring formula. This is the direction that we're using for gravity, so that has to be in that direction to use the gravity formula. We're not using coordinates because we're not breaking vectors into components anymore. So this is my initial drawing to determine energies that this block would have. And then sometime later, the block is now up like this. It has a final velocity of 0 meters per second, and it's at some distance y, which I don't know. Now, I'm going to draw that over here as well. So what we're talking about is that this distance is x, f minus xi, and this distance is y minus 0. I call it yf. So those two are related, and they're related by trigonometry with this angle of 30 degrees. I'll need that later on in the problem. And let me finally put down that this is the final. It is essential that you go through these sort of steps on harder problems. While it may be possible to write a formula off your head on a simple problem if you're very bright, it will not be able to do it if the problem gets harder. So go through the steps, draw an energy diagram. Things you need to know is the initial position in y for gravitation, the initial x position for a spring, and you'll need to know the velocity in order to calculate kinetic energy. Now, the final energy. Well, the final energy is the final kinetic plus the final potential. There is no kinetic, it's not moving. Initially, it had some initial kinetic plus initial potential, but the kinetic was again 0 because it was not moving. What type of potential does it have at the end? The only type of potential it has is gravity. Gravitational potential energy is mg yf. What type of potential energy did it initially have? Well, it was at y equals 0 because that was my choice. It has no gravitational, but it has spring. 1/2 k xi squared. Want to solve for y sub f. Y sub f is equal to k x sub I squared over 2 mg. Let's see, I think I have everything I need in this problem. I have to go back up and look. Let's see, I have m is 5 kilograms. I have k, 200 newtons per meter, and I have x is 0.6 meters. So putting that in, let's see, 200 newtons per meter minus 0.6 meters, but I'm squaring that, over 2 times, let me go back and check, see what the mass of my block was, 5 kilograms, 9.8 meters per second squared. Punch all that in. So let's see, 200 times 0.6 squared divided by 10 divided by 9.8. It moves 73.5 centimeters, or 0.735 meters, assuming that I punched the calculator correctly. And I believe that I have. Now, I need to find L, the distance that it goes up the incline. I believe that's what was asked. They didn't ask me how high did it go. They said how far up the incline. So what they want to know is they want to know this distance here, which I'll call L. That's just xf minus xi. And what I know is this part here, which, let me go back and get my 0.735 meters. And I know this angle is 30 degrees, so I can use trigonometry to find that. L is equal to y sub f over the sine of 30 degrees. Sine of 30 is a half, so that'd be 2yf, which should be approximately 0.735 times 2, 1.47 meters. Nothing really unique about this problem. It just shows you that you have to calculate all the energies. Notice something else about the problem. I was able to choose my initial y position here as 0 and then do the y at the top as being the new height, rather than choosing, for instance, this location as y equals 0. That wise choice saved me some time and difficulty because it connected this side, which is what I needed, to that length, which I wanted to find. If they'd asked me to do it from the time it left x equals 0, I might have made a different choice. A wise choice on your zero potential energies can simplify your calculations. All right, that's it for this problem. We'll see you on another video.